What if everything you know about the beginning of the universe is just the tip of an unimaginable cosmic iceberg? Picture this, an entire cosmos, all the stars, galaxies, and even time itself, popping into existence not with a bang, but through a quantum loophole so strange it defies common sense. This is the wild frontier of quantum tunneling, where particles cheat the rules of physics to make the impossible possible. And today, we're diving into 30 mind-blowing theories that suggest our universe might have started exactly this way, with a single, universe-sized quantum jump. From the multiverse to black holes rewriting reality, each theory we'll explore is more astonishing than the last. So buckle up, because by the end of this journey, you'll never look at the night sky the same way again. Ready to have your mind stretched? Let's begin. Now let's peel back the layers of our first theory, where the universe's grand entrance might have been quieter than you'd expect. No fireworks, no explosion, just a whisper in the void. Imagine a place of perfect nothingness, not even empty space, just pure potential. This is where quantum mechanics takes center stage. According to Heisenberg's uncertainty principle, even in a total vacuum, particles can pop in and out of existence like cosmic fireflies, borrowing energy from nowhere and returning it almost instantly. But what if one of these tiny fluctuations didn't just flicker? What if it tunneled through an energy barrier, defying the odds to become something permanent? That's the daring idea behind quantum fluctuation as the cosmic trigger. In this scenario, our entire universe could be the result of a single, unimaginably lucky quantum event, a tiny blip in the void that refused to fade away. Think of it like a bubble forming in a boiling pot, except the pot is the fabric of reality itself, and the bubble is everything we know. The math behind this isn't just speculative, it's grounded in the same principles that make transistors in your phone work. And if it sounds like getting something from nothing, well, that's the magic of quantum mechanics. Energy isn't created or destroyed, it's borrowed, balanced, and sometimes, if the conditions are just right, it becomes the foundation for a cosmos. So next time you look up at the night sky, remember, the universe might not have needed a match to ignite. It could have simply tunneled into being. Now let's take a step beyond our own universe and into something even grander, the multiverse. Picture an endless cosmic ocean where countless bubbles float, each one a separate universe with its own unique laws of physics. Our universe could be just one of these bubbles, born from a quantum tunneling event in a much larger, perhaps infinite multiverse. This is the Multiverse Seed Hypothesis, and it flips the script on how we think about origins. Instead of the universe appearing from nothing, it might have emerged from a pre-existing reality, like a sprout breaking through soil. The idea ties back to quantum tunneling, where particles overcome energy barriers they shouldn't be able to cross. On a cosmic scale, this could mean our entire universe tunneled into existence from another region of space-time, carrying with it the conditions for stars, galaxies, and us. Stephen Hawking explored this in his work on quantum cosmology, suggesting that the laws of physics we know might just be local rules unique to our bubble, while the wider multiverse operates on entirely different principles. This theory stands in contrast to eternal inflation, where universes endlessly sprout from an expanding fabric of space-time without tunneling. Here, the multiverse isn't a quiet quantum event but a chaotic, ever-growing foam of universes. Yet both ideas share a wild implication. Our universe might not be special, just one possibility among countless others. So if you've ever wondered why the constants of nature seem perfectly tuned for life, the answer might be simple: we're in the bubble where the numbers lined up. And somewhere out there, other versions of reality could be playing by entirely different rules. Now, let's shift our focus to an idea that turns the concept of nothingness on its head: the zero-energy universe. Imagine the universe as a cosmic ledger where every bit of positive energy is perfectly balanced by negative energy, adding up to zero. This delicate equilibrium could be the key to understanding how everything we see around us emerged from what seems like nothing at all. Lawrence Krauss, a theoretical physicist, has championed this idea, suggesting that the universe's total energy might sum to zero when you account for all the positive energy in matter and the negative energy in gravity. Think of it like taking out a loan. The universe borrowed energy to create itself, but the debt is exactly cancelled out by the gravitational pull holding it all together. In this scenario, quantum tunneling wouldn't need to violate energy conservation because, on the grandest scale, nothing was actually created or destroyed. This theory flips the script on the old question, why is there something rather than nothing? Instead, it proposes that nothing might inherently contain the potential for something. The vacuum of space isn't truly empty, it's a seething sea of quantum fluctuations where particles pop in and out of existence. Under the right conditions, these fluctuations could tunnel into a stable state, birthing an entire universe. So, if the numbers add up just right, the cosmos could be the ultimate free lunch, a vast, intricate structure that costs zero energy to create. And that raises another mind-bending thought. If our universe is a zero-energy quantum tunnel, could there be others just like it, each balancing their own cosmic books? The answer might lie in the fine print of physics itself. Now, let's step into the realm of higher dimensions where the rules of our familiar universe start to bend. String theory paints a picture of reality not as point-like particles, but as tiny, vibrating strings, each note they play corresponding to a different particle or force. But here's where it gets wild. These strings exist in a vast landscape of possible vacuum states, like an infinite cosmic menu of universes with different physics. Quantum tunneling could be the mechanism that allows our universe to hop from one vacuum state to another, like a bubble shifting in a frothy sea of possibilities. And then there's M-theory, the grander sibling of string theory, which introduces the idea of branes, short for membranes. Picture these branes as giant, floating sheets in higher dimensional space. When two of them collide, the energy released could be the spark that ignites a new universe. It's like cosmic bumper cars, where a crash doesn't mean destruction but creation. Some physicists speculate that our Big Bang might have been the aftermath of such a collision, a quantum tunnel from a higher dimensional event into the space-time we know today. What's fascinating is how these theories blend the very large and the very small. The same quantum processes that govern subatomic particles could shape the fate of entire universes. If string theory's landscape is real, then our universe might just be one note in an endless symphony of cosmic possibilities. And if branes are out there, colliding in dimensions we can't even perceive, then the birth of our universe might have been just one ripple in a much bigger pond. The question is, are we alone in this multiverse, or is it buzzing with other bubbles, other bangs, other versions of reality? The math hints at an answer, but the full story is still vibrating somewhere in the strings. Now, let's take a different turn and explore a theory that reimagines the very beginning of everything. The Hawking-Hartle No-Boundary Proposal offers a radical alternative to the traditional Big Bang singularity. Instead of a violent explosion from an infinitely dense point, this theory suggests the universe began with a smooth, finite geometry, like a shuttlecock's rounded base with no sharp edges or boundaries. Quantum tunneling plays a key role here. Imagine the universe not as a sudden burst from nothing, but as a gentle transition from a timeless, spaceless state into the expanding cosmos we know today. It's like a bubble forming in a calm pond, no abrupt rupture, just a seamless emergence. The no-boundary condition means there's no need for a before the Big Bang, because time itself smoothly curves into existence, much like how the Earth's surface has no edge even though it's finite. This idea flips the script on cosmic origins. Instead of a singularity where physics breaks down, the universe could have tunneled into being from a state where the concepts of space and time simply didn't apply. It's a bit like trying to find the starting point on a circle. There isn't one because the geometry is self-contained. Hawking-Hartle's proposal gives us a universe without a hard beginning, just a graceful quantum leap into reality. So, if this theory holds, the Big Bang wasn't a bang at all. It was more like a cosmic whisper, a quiet tunneling into existence. And that changes everything about how we think of the universe's first moments. No fiery explosion, no singularity, just a smooth, elegant transition from nothingness to everything. The question is, does this elegant math match reality? That's a mystery still waiting to be unraveled. Now, let's shift gears to a theory that turns the idea of a one-time Big Bang on its head. Loop quantum gravity, or LQG, suggests something extraordinary. What if our universe wasn't born from nothing, but instead bounced back from a previous collapsing cosmos? Picture spacetime not as a smooth continuum, but as a fabric woven from tiny, discrete loops. These loops are so small that they're like the pixels of reality, giving spacetime a granular structure. This granularity changes everything. In LQG, when a dying universe collapses under its own gravity, it doesn't just vanish into a singularity. Instead, the quantum nature of spacetime kicks in, acting like a cosmic trampoline. The universe reaches a point where the loops resist further squeezing, creating a repulsive force so powerful that it triggers a quantum tunnel into a new expanding universe. It's as if the universe hit a reset button, recycling itself through a cosmic rebound. At the heart of this idea are Ashtakar's equations, which describe how spacetime's loops behave under extreme conditions. These equations show that gravity, when pushed to its limits, doesn't just collapse, it rebounds. This opens the door to cyclical cosmology, where universes might go through endless cycles of expansion, collapse, and rebirth. No need for a mysterious beginning or a lonely end, just an eternal dance of cosmic renewal. So, if LQG is right, the Big Bang wasn't the start of everything. It was merely the latest bounce in an endless cycle, a quantum leap from one universe to the next. The question is, could we ever find evidence of a universe before ours? That's a puzzle scientists are still trying to solve, but one thing's clear: the cosmos might be far more resilient and far more cyclical than we ever imagined. Now, let's venture into the strange and unsettling realm of quantum instability, where the universe's very foundations might be more fragile than we think. First up is dark energy, the mysterious force accelerating the expansion of the cosmos. Some theories suggest dark energy could be a relic of quantum tunneling, a leftover imprint from the universe's earliest moments. Imagine it as a cosmic echo, a faint whisper of the quantum leap that birthed everything. If true, dark energy isn't just pushing galaxies apart, it's a living fossil of the universe's explosive beginning. Next, we have false vacuum decay, a scenario that sounds like science fiction but is taken seriously by physicists. Picture the universe sitting in a precarious state, like a ball balanced on the edge of a hill. Right now, our cosmic vacuum seems stable, but it might actually be a false vacuum, a temporary low-energy state. If a quantum fluctuation tunnels the universe into a true vacuum, the laws of physics as we know them could rewrite themselves in an instant. The result, a bubble of destruction expanding at the speed of light, erasing everything in its path. It's the ultimate cosmic reset button, and we wouldn't see it coming. Then there's the mind-bending idea of Boltzmann branes. Named after physicist Ludwig Boltzmann, these are hypothetical self-aware entities that could emerge from random quantum fluctuations. Think of them as cosmic accidents, branes popping into existence, complete with false memories, convinced they're living in a real universe. If quantum tunneling can create entire universes, why not a lone, conscious observer out of thin air? It's a bizarre twist on the nature of reality, suggesting that our own existence might be a fleeting fluctuation in an endless sea of randomness. Together, these theories paint a picture of a universe where stability is an illusion, and quantum tunneling lurks beneath the surface, ready to rewrite reality at any moment. Whether it's dark energy's hidden origins, the existential threat of false vacuum decay, or the eerie possibility of Boltzmann branes, one thing's clear: the cosmos is far stranger and far more unpredictable than we often assume. Now, let's turn our attention to a theory that reimagines the universe's timeline in a breathtaking loop: Penrose's conformal cyclic cosmology. Picture this: instead of a one-time Big Bang, the cosmos undergoes endless cycles, each beginning with a quantum tunneling event. In this model, black holes play a starring role. As they slowly evaporate over unimaginable spans of time, they release energy that resets space-time itself, paving the way for a new eon or cosmic epoch. What's truly fascinating is how quantum tunneling fits into this grand cycle. The transition from one eon to the next isn't a violent collision or a chaotic explosion. It's a smooth, almost elegant leap made possible by the strange rules of quantum mechanics. Think of it as the universe hitting a cosmic refresh button, where the remnants of black holes from a previous cycle become the seeds for a new one. Penrose's idea suggests that the very fabric of reality is recycled, with quantum tunneling acting as the invisible hand guiding the process. To visualize this, imagine a conformal diagram, a map of space-time where infinity is squeezed into a finite space. In this diagram, the end of one eon seamlessly connects to the beginning of the next, like a Möbius strip of existence. Quantum tunneling bridges the gap, ensuring that information and energy aren't lost but transformed. It's a radical departure from the idea of a linear universe, offering instead a vision of eternity woven into the cosmos's DNA. So, if Penrose is right, our universe isn't just a one-off event. It's part of an endless dance of creation and renewal, with quantum tunneling as the silent choreographer. And that raises a tantalizing question: could traces of past eons still linger in the cosmos today, hidden in the faint whispers of black hole echoes? The answer might just rewrite our understanding of time itself. Now, let's shift our perspective to something even more mind-bending: the idea that our entire universe might be a hologram. Not the sci-fi kind, but a cosmic one, where all the information we see in 3 dimensions could have tunneled from a 2-dimensional boundary. This is the heart of the holographic principle, a theory championed by physicist Leonard Susskind. At its core, the principle suggests that everything we experience, stars, galaxies, even you and me, might just be a projection of data encoded on a distant, flat surface. Think of it like a movie screen. The images appear 3-dimensional, but they're actually coming from a 2-dimensional film. In this case, the film could be the edge of the universe itself, with quantum tunneling acting as the projector, translating that data into the reality we know. Black holes play a key role here. When matter falls into a black hole, it doesn't just vanish. Its information gets smeared across the hole's event horizon, a 2-dimensional surface. Susskind and others realize that this isn't just a quirk of black holes. It might be a fundamental feature of space-time. If the universe can store all its information on a 2D boundary, then quantum tunneling could be the mechanism that brings it to life in 3D, like a cosmic pop-up book. What's wild is that this idea isn't just speculation, it's backed by math. The holographic principle ties into black hole entropy, which measures the amount of information a black hole can hold. The equations suggest that the maximum entropy in any region of space isn't determined by its volume, but by its surface area. That's a huge clue that reality might be more surface than substance. So, if the holographic principle is correct, our universe's origin story might not be about a singularity exploding into 3 dimensions. It could be about information tunneling from a flat, shadow realm into the rich, layered world we see today. And that leaves us with a haunting question: if we're just projections, what or who is holding the projector? But here's a twist. What if our universe's very existence isn't just random, but the result of a cosmic selection process? This brings us to quantum Darwinism, a theory that suggests the laws of physics we take for granted might have been chosen through quantum tunneling from a vast multiverse. Imagine a cosmic game of survival where only universes with the right conditions like ours end up lasting long enough for observers like us to emerge. At the heart of this idea is the anthropic principle, which argues that the universe's constants seem fine-tuned for life because, well, we're here to notice them. Quantum Darwinism takes it further. In a sea of infinite universes, each with different physical laws, only those capable of sustaining complexity through processes like quantum tunneling would produce observers. The rest, they'd fizzle out unnoticed. Think of it like a forest. Countless seeds are scattered, but only those that land in the right soil grow into trees. Similarly, countless universes might tunnel into existence, but only those with stable atoms, habitable planets, and the right balance of forces would ever be observed. It's not that the universe was designed for us, it's that we're the ones left standing in a cosmic lottery where the winners get to tell the story. Critics argue this leans too heavily on chance, but supporters point to the eerie precision of our universe's constants. Why does gravity have exactly the strength it does? Why do protons and electrons balance so perfectly? Quantum Darwinism offers a possible answer, because any slight variation would mean no stars, no planets, and no one to ask the question. So, if this theory holds, our universe isn't just a random quantum fluctuation, it's a survivor, a rare bubble where tunneling events conspired to create the perfect stage for life. And that raises another dizzying thought. In the infinite multiverse, are there other winners out there wondering the same thing? Now, let's take a leap into the wild world of wormholes. Picture this. What if the universe didn't just pop into existence from nothing, but instead emerged from a cosmic tunnel, a quantum wormhole? This is the heart of Theory 14, the ER equals EPR idea, where two of Einstein's most mind-bending concepts collide. Einstein and his colleague Nathan Rosen once proposed that black holes could be connected by bridges later dubbed Einstein-Rosen bridges or wormholes. Fast forward to modern physics, and Juan Maldacena and Leonard Susskind suggested something even stranger. These wormholes might be forged by quantum entanglement, the same spooky connection that links particles across vast distances. Here's how it could work. Imagine two entangled particles like a pair of cosmic twins. No matter how far apart they are, changing one instantly affects the other. Now scale that up. What if the entire universe began as a quantum wormhole, a tunnel woven from entanglement itself? In this scenario, the Big Bang wasn't a singularity. It was the mouth of a wormhole, a bridge from some deeper quantum reality. This idea isn't just science fiction. Experiments in quantum gravity are testing whether entanglement really can create microscopic wormholes in the fabric of space-time. If they're right, our universe might be the ultimate example of quantum connectivity, a cosmic not tied by the laws of physics. Critics ask, how could something so vast emerge from such a tiny quantum link? Supporters point to holography, where the entire universe could be encoded on its boundary, like a 3D movie projected from a 2D screen. If that's true, then a wormhole might just be the universe's way of stitching itself together from the quantum code up. So if ER equals EPR holds water, our universe isn't just a place, it's a connection, a thread in the grand tapestry of reality. And that leaves us wondering, if we're inside a wormhole, where does the other end lead? Now let's shift gears and dive into something even more mind-bending. What if our universe isn't just a cosmic accident, but a digital simulation or a mathematical structure? Theories 15 and 16 take us down the rabbit hole of digital and abstract origins, where reality might be nothing more than code or pure logic. First up is the simulated universe hypothesis, popularized by philosopher Nick Bostrom. Here's the idea. if advanced civilizations could one day create hyper-realistic simulations of entire universes, complete with conscious beings, then the odds are we're living in one of those simulations rather than the original, base reality. Think of it like a video game so advanced the characters inside don't even realize they're part of a program. Quantum tunneling in this scenario could be the glitches or background processes of the simulation, tiny bursts of code that allowed our universe to boot up from nothing. But what if reality isn't digital at all, but purely mathematical? That's where Max Tegmark's mathematical universe hypothesis comes in. Tegmark argues that our universe isn't just described by math, it is math. Every particle, every force, even space and time, are just structures in an abstract mathematical space. In this view, quantum tunneling could be the universe solving an equation, jumping from one mathematical state to another like a cosmic calculator finding a new solution. Critics of the simulation theory ask, where's the evidence? Supporters point to oddities in quantum mechanics, like the observer effect, where particles behave differently when measured, almost as if the simulation is optimizing processing power. Meanwhile, skeptics of the mathematical universe argue that math is a tool we use to describe reality, not reality itself. Yet both theories share a wild implication. If they're true, then the Big Bang wasn't a physical event, but a logical or computational one. Our universe might be less like a firework exploding and more like a program launching or an equation balancing itself. So, are we living in a supercomputer's dream, or is existence itself just a giant math problem? Either way, it makes you wonder what's running the code or who's holding the pencil. Now, let's take a step into the strange world of time itself. What if quantum tunneling didn't just create our universe, but also gave time its direction? Theory 17 suggests exactly that. Quantum tunneling might be the hidden force behind time's arrow, the reason entropy always increases and why we remember the past but not the future. Picture Schrödinger's famous cat, both alive and dead in its box until someone opens it. Now, imagine that box is the entire universe. Quantum tunneling could be the moment the universe chooses a state, breaking the symmetry of time and setting entropy in motion. In other words, tunneling might have nudged the cosmos from a state of perfect balance into one where disorder grows, giving time its one-way street. Here's how it works. At the quantum level, particles can tunnel through barriers they shouldn't be able to cross, seemingly defying the usual rules. If this happened on a cosmic scale during the universe's birth, it could have tipped the scales from a timeless, symmetrical state into one where time flows forward. Think of it like a ball sitting at the top of a hill. Quantum tunneling gave it the tiny push needed to roll down, creating the irreversible flow we experience now. Critics might argue that time's arrow is just a result of statistical probability, not quantum weirdness. But supporters of this theory point out that without tunneling, there'd be no first move to break the symmetry. It's like a cosmic game of dominoes. Tunneling was the flick that started the chain reaction, leading to the universe we know today. So, next time you notice how time only moves forward, remember, it might all trace back to a single quantum jump, a cosmic version of Schrödinger's cat deciding once and for all which way time would run. Now, let's shift our gaze to the mysterious realm of supersymmetry, a theory that could hold the key to understanding how quantum tunneling shaped the universe's very fabric. Theory 18 proposes that the decay of supersymmetric particles or sparticles might have triggered a cosmic phase transition through quantum tunneling, catapulting the universe into the state we observe today. Supersymmetry, often called SUSY for short, suggests that every known particle has a heavier, unseen partner. These particles could have played a crucial role in the early universe. Imagine a cosmic seesaw. When these particles decayed, their energy might have tunneled through a quantum barrier, tipping the universe from one phase of existence into another. This transition could explain why the cosmos looks the way it does, from the forces governing matter to the very structure of spacetime. Scientists at CERN are hunting for signs of these elusive particles using the Large Hadron Collider. If they're found, it would bolster the idea that supersymmetry played a pivotal role in the universe's quantum origins. Think of it like uncovering a hidden chapter in a cosmic history book, one where particles acted as the architects of reality itself. Some skeptics argue that supersymmetry remains unproven, and without direct evidence, it's just an elegant hypothesis. But supporters counter that the math behind SUSY is too compelling to ignore, solving puzzles like dark matter and the hierarchy problem in physics. Whether or not particles are discovered, this theory reminds us that the universe's first moments might have been shaped by particles we're only beginning to imagine. So, as physicists continue their search, we're left wondering, did supersymmetry's hidden dancers choreograph the quantum leap that brought our universe into being? The answer might lie in the next collision deep underground at CERN. Now, let's turn our attention to one of the most elusive particles in the cosmos, the neutrino, and how it might have played a starring role in the universe's quantum origins. Theory 19 dives into the idea that an ultra-dense sea of neutrinos could have tunneled into a high-energy state, sparking the explosive expansion we call the Big Bang. Neutrinos are ghostly particles that barely interact with matter, passing through entire planets as if they weren't even there. But in the extreme conditions of the early universe, they might have behaved very differently. Picture a vast ocean of neutrinos packed so tightly that quantum tunneling allowed them to suddenly leap into a higher energy state. This jump could have released enough energy to kickstart cosmic inflation, setting the stage for everything we see today. What makes this theory even more intriguing is the mystery of neutrino oscillations. The way neutrinos switch between different types as they travel. This strange behavior hints at physics beyond our current understanding, suggesting neutrinos might hold secrets about the universe's first moments. If a neutrino condensate did trigger expansion, it could explain why these particles are so light yet so abundant, like cosmic breadcrumbs left over from the dawn of time. Of course, this idea is still speculative. Neutrinos are notoriously hard to study, and we've only scratched the surface of their properties. But experiments like the Deep Underground Neutrino Experiment, or DUNE, are designed to probe these mysteries further. Imagine uncovering a hidden link between neutrino behavior and the birth of spacetime itself. It would rewrite the story of our cosmic origins. So, while we don't yet have proof that neutrinos ignited the universe, the possibility reminds us how much we still have to learn. These tiny, nearly massless particles might just hold the key to one of the biggest questions of all: how everything began. And as detectors around the world keep searching, we inch closer to unlocking their secrets. Now, let's venture into the realm of the truly exotic, where quantum fields we've never directly observed might hold the answers to cosmic mysteries. Theories 20 through 22 take us into the world of action fields, quintessence, and phantom energy, three hypothetical players that could explain why the universe is expanding faster and faster. First up, actions. These are ghostly particles born from quantum field theory, originally proposed to solve a puzzle in particle physics. But here's the twist: actions might also form an invisible, universe-spanning field. If this field underwent quantum tunneling in the early cosmos, it could have released energy that later morphed into dark energy, the mysterious force driving cosmic acceleration. Picture an action field like a stretched rubber band suddenly snapping, unleashing energy that still lingers today. Then there's quintessence, a dynamic field that changes over time. Unlike a constant dark energy, quintessence could have tunneled between different energy states, alternately speeding up and slowing down expansion. Think of it as a cosmic thermostat, fine-tuning the universe's growth spurt. Some models even suggest quintessence might one day reverse course, collapsing the universe in a big crunch. Finally, phantom energy, the wild card. This hypothetical field grows stronger as the universe expands, potentially tearing space-time apart in a big rip. If phantom energy emerged from quantum tunneling, it could explain why expansion keeps accelerating. Imagine a runaway train where each mile it travels makes the engine more powerful eventually. Nothing could hold it together. What ties these theories together? They all rely on exotic quantum fields tunneling into existence, reshaping the cosmos in ways we're still trying to understand. While none have been proven yet, experiments like the Action Dark Matter Experiment, or ADMX, are hunting for clues. Whether actions, quintessence, or phantom energy hold the answer, one thing's clear: the universe's acceleration is a puzzle with quantum roots, and the solution might be stranger than we've dared to imagine. Up next, we'll explore an even bolder idea: that our universe might have burst from the other side of a black hole. Stay tuned. Now, let's take a leap into one of the most mind-bending ideas yet. What if our universe didn't just tunnel into existence, but actually burst out of the other side of a black hole? Theory 23 flips the script entirely, suggesting that our cosmos might be the result of a black hole transforming into its opposite, a white hole. Here's how it could work. In Einstein's general relativity, a black hole is a one-way street. Matter and energy fall in, but nothing escapes. But some theories propose that deep inside a black hole's singularity, quantum effects could cause a rebound, turning it into a white hole, a cosmic exit where matter and energy pour outward instead of vanishing. If this transition happened via quantum tunneling, our universe could have erupted from a white hole's explosive birth. Picture it like a cosmic phoenix rising from the ashes of a collapsed star in another reality. Now contrast this with loop quantum gravity's take. In LQG, space-time isn't smooth, it's made of tiny, woven loops. When a black hole reaches maximum density, these loops might resist further collapse, causing a bounce. Instead of a singularity, the black hole tunnels into a white hole, bridging two universes. Think of it like a rubber band stretched to its limit. Snap back, and you've got a new beginning. So, which idea holds more weight? The white hole bridge leans on quantum gravity's quirks, while LQG offers a concrete mechanism. Both suggest our universe might be the other side of a cosmic coin, a rebirth from collapse. And while we've never observed a white hole, some physicists speculate that certain gamma-ray bursts or even the Big Bang itself could be evidence of one. Up next, we'll zoom in even further, to the fabric of space-time itself, where the universe might have emerged from a quantum leap between discrete atoms of reality. Stay with us. Now, let's shrink our perspective down to the very building blocks of reality itself. Theory 24 takes us into the world of causal set theory, where space-time isn't a smooth, flowing fabric. It's more like a mosaic of tiny, indivisible pieces. Imagine the universe as a digital image, starting out as a blurry, pixelated mess before sharpening into the high-definition cosmos we see today. In this framework, space-time is made up of discrete atoms of reality, connected in a vast, intricate web. These fundamental units don't exist in a continuous flow, but instead form a causal set, a structure where each point is linked by cause and effect. Quantum tunneling, then, could be the process that bridges these isolated points, stitching them together into the seamless continuum we experience. Think of it like flipping through a flipbook. Individually, each page is just a static image, but when you move fast enough, the illusion of motion emerges. What's fascinating here is how this idea challenges our classical view of space-time. Instead of a pre-existing stage where events unfold, the stage itself emerges from these quantum jumps. It's as if the universe booted up from a glitchy, fragmented state before stabilizing into the smooth expanse we know. Some researchers even suggest that remnants of this pixelated past might linger in the fabric of reality, tiny fluctuations in gravity or light that could one day be detected. So, how does this fit with the bigger picture? If causal set theory is correct, then the first quantum tunneling event might not have been a leap from nothing to something, but from chaos to order, a cosmic upgrade from disconnected dots to a coherent universe. And while this idea is still speculative, it offers a tantalizing glimpse into how the deepest layers of reality might operate. Next, we'll explore an even more abstract possibility, where space-time itself wasn't just born from quantum tunneling, but from a mathematical equation coming to life. Stay tuned. Now, let's take a step into the realm where mathematics and physics blur into one. Theory 25 introduces us to Elaine Kahn's groundbreaking idea of non-commutative geometry, a framework where space-time might not have started as a smooth, continuous fabric at all. Instead, it could have emerged from something far more abstract, a world where even the rules of geometry were still up for grabs. Picture this: before the universe had dimensions, distances, or even a clear notion of here and there was a chaotic, pre-geometric state. In this primordial soup, the very algebra that defines space-time, the mathematical relationships between points hadn't yet settled into the familiar commutative rules we know today. Normally, if you multiply two numbers, the order doesn't matter. 3 times 4 is the same as 4 times 3. But in this early phase, the algebra might have been non-commutative, meaning the sequence of operations could have changed the outcome. Quantum tunneling, then, becomes the mechanism that bridges this wild, unstructured state to the orderly geometry we recognize. It's as if the universe performed a mathematical phase transition, tunneling from a fuzzy, undefined reality into one with clear spatial relationships. Think of it like a symphony tuning up before a performance, individual notes clashing and overlapping until suddenly harmony emerges. What's truly mind-bending is how this idea redefines the birth of space-time. Instead of space and time being fundamental, they're almost like emergent properties arising from deeper algebraic structures. Some physicists speculate that traces of this pre-geometric phase might still linger in quantum gravity effects or even in the way black holes process information. So, if Kahn's vision holds, the first quantum tunneling event wasn't just about creating particles or energy. It was about forging the very rules of reality from raw mathematics. And while this remains a speculative frontier, it challenges us to rethink what it means for the universe to begin at all. Up next, we'll dive into another radical idea where space-time wasn't born from algebra, but from a cosmic network of quantum connections. Stay curious. Now, imagine a universe where space itself wasn't always smooth and continuous, but instead began as a tangled web of quantum connections. This brings us to Theory 26, where we explore the radical idea of quantum gravity, a model suggesting space-time might have emerged from a cosmic network of quantum bits, or graphity, tunneling into the geometry we know today. Picture a vast, chaotic lattice where each point is connected to others in a constantly shifting dance. In this early phase, the universe wasn't made of points in space, but of relationships like a cosmic game of connect the dots where the dots themselves don't matter as much as how they link together. Quantum tunneling could have been the key that unlocked this frozen network, allowing it to transition into the fluid, dynamic space-time we experience now. What's fascinating is how this ties into loop quantum gravity's spin network structures that represent space as woven from threads of quantum information. In both ideas, the universe's geometry isn't handed to us on a silver platter. It's something that crystallizes from deeper, more fundamental interactions. Think of it like ice forming on a pond. The water molecules don't know. They're creating a solid surface until the right conditions snap them into place. Some researchers even speculate that remnants of this gravity phase might still echo in the fabric of space-time, perhaps hiding in the way black holes store information or how quantum particles entangle across distances. It's a reminder that the universe's first quantum tunneling event might not have just shaped matter or energy. It could have woven the very stage they perform on. Next, we'll turn to a theory where time itself emerges not from clocks or motion, but from the quantum whispers of heat and disorder. Stay with us, the journey only gets stranger from here. Now let's step into a world where time itself isn't a fixed backdrop but something that emerges from the chaos of quantum heat. This is Theory 27, the thermal time hypothesis, where physicist Carlo Rovelli proposes that time might not be fundamental at all. Instead, it could be a byproduct of quantum thermal fluctuations like frost forming on a windowpane. Picture the early universe as a seething ocean of energy where particles jostle and collide in a frenzy. In this state, there's no past or future, just a swirling mess of probabilities. But as quantum tunneling nudges the system toward stability, something remarkable happens. Order begins to crystallize from the chaos, and with it, the arrow of time emerges. Think of it like watching steam condense into droplets. The randomness of individual molecules gives way to a clear direction, marking the flow from disorder to order. What's mind-bending here is that time, as we experience it, might just be a side effect of this quantum cooling process. Rovelli's idea suggests that our perception of time's passage, the ticking of clocks, the aging of stars, is really just the universe settling into a state where entropy can rise. It's not that time exists out there. It's more like a story we tell to make sense of the universe's gradual unraveling. And just like ice crystals need a seed to form, quantum tunneling could have been the trigger that set this thermal time into motion. One tiny fluctuation, one cosmic nudge, and suddenly the universe had a before and after. It's a humbling thought that the very fabric of time might owe its existence to the same quantum whims that birthed space and matter. Up next, we'll dive into theories where the universe's origins might hinge on something even more elusive, the role of consciousness itself. Trust me, you won't want to miss this. Now, let's venture into one of the most provocative ideas in quantum cosmology, the notion that consciousness itself might have played a role in the universe's birth. This brings us to theories 28 and 29, where the line between observer and observed blurs in ways that challenge everything we think we know about reality. First up is the von Neumann-Wigner interpretation, which flips the traditional view of quantum mechanics on its head. Instead of particles existing in definite states until measured, this theory suggests that consciousness is what causes the so-called collapse of quantum probabilities into a single outcome. Imagine the early universe as a fog of infinite possibilities waiting for an observer, perhaps even the first flicker of awareness, to pin it down into the reality we know. It's as if the universe needed someone to look at it to truly exist. Then there's John Wheeler's It from Bit participatory universe, a radical idea that takes this even further. Wheeler proposed that the physical world, the it, might emerge from information, the bits. In this view, quantum tunneling wasn't just a random event but a kind of cosmic computation, where the act of observation itself helped shape the universe's structure. Think of it like a cosmic game of 20 questions, where every interaction, every measurement, narrows down the possibilities until reality crystallizes. What's wild about these theories is how they bridge physics and philosophy. If consciousness or observation played a role in the universe's origins, does that mean reality is, in some sense, a collaborative project? Could the first quantum tunnel have been nudged into existence by the very act of being witnessed? It's a dizzying thought, one that makes you wonder whether we're just passengers in the cosmos or active participants in its unfolding story. And speaking of participation, our next theories take this even deeper, exploring how the fabric of space-time might owe its existence to something even more fundamental: pure mathematics. Stay tuned, because things are about to get even stranger. Now, let's pull all these mind-bending ideas together with our final theory, one that might just tie everything up in a cosmic bow. Theory 30 takes us to the cutting edge of physics, where quantum gravity itself could hold the key to the universe's first quantum tunneling event. Picture this: what if space-time didn't just appear out of nowhere, but tunneled into existence from a state where gravity and quantum mechanics finally shake hands? That's the promise of asymptotically safe gravity, a framework where the laws of physics smooth out at ultra-high energies, allowing space-time to emerge seamlessly. Think of it like a frozen lake thawing, the cracks and chaos of quantum uncertainty gradually settling into the smooth, predictable fabric we know today. And here's where it gets even more compelling. Recent insights from LIGO, the Laser Interferometer Gravitational Wave Observatory, hint that space-time might not be as rigid as we once thought. Ripples in the fabric of the universe, gravitational waves, could carry echoes of those primordial quantum jumps, like faint whispers from the moment reality first flickered to life. If we're lucky, future detections might even catch a signature of spacetime's birth cry, a tremor left over from that initial tunnel. So what does this mean for the big picture? If quantum gravity truly orchestrated the universe's first leap into existence, it wouldn't just solve the mystery of the Big Bang, it would rewrite our understanding of cause and effect itself. No need for a before or a first mover. The universe could be its own origin story, a self-contained loop where the question, what started it all, melts away into the quantum foam. And with that, we've reached the end of our journey through 30 wild theories. But don't go anywhere just yet, because up next we're tackling the biggest misconceptions about quantum tunneling, and you won't want to miss the truth behind the myths. Now, let's clear up some of the biggest misunderstandings about quantum tunneling, because when it comes to the bizarre rules of the quantum world, myths tend to spread faster than facts. First up, the idea that quantum tunneling breaks the law of energy conservation. It's easy to see why this myth sticks around after all. How can a particle suddenly appear on the other side of a barrier it shouldn't have the energy to cross? But here's the twist: tunneling doesn't actually violate energy conservation. Thanks to Heisenberg's uncertainty principle, particles can borrow energy from the vacuum for incredibly short times, like a cosmic IOU that gets repaid almost instantly. Feynman diagrams show this beautifully, with virtual particles popping in and out of existence, balancing the books so energy is always conserved in the grand scheme. Another common mix-up is thinking tunneling is just a mathematical trick, not something that happens in the real world. Tell that to your smartphone. Tunnel diodes are a key part of modern electronics and radioactive decay, where particles tunnel out of atomic nuclei, is proof this phenomenon shapes the universe every single day. Then there's the wild claim that tunneling means anything can teleport anywhere. Not quite. The odds drop exponentially with distance, so while an electron might hop a tiny barrier, your chances of quantum leaping through a wall are, well, zero. And finally, no, tunneling doesn't let time run backward or break causality. Those fleeting quantum jumps stay neatly within the rules, even if they bend our everyday intuition. So next time someone says tunneling defies physics, you'll know the truth. It's not magic, just nature playing by its own extraordinary rules. And speaking of rules, stay tuned as we dive into the real-world experiments trying to recreate the universe's first quantum leap in labs today. Now, let's step into the cutting-edge world of experiments where scientists are recreating the universe's first quantum leaps right here on Earth. Imagine trying to study the birth of the cosmos, something that happened billions of years ago, without a time machine. That's where lab analogs come in, offering a backdoor to understanding quantum tunneling on a cosmic scale. One groundbreaking approach involves superfluid vacuum experiments. Picture a fluid with zero friction, where particles move without resistance, a perfect playground to simulate the strange conditions of the early universe. Researchers chill helium to near absolute zero, creating a superfluid that mimics the quantum vacuum. In this state, they can observe how tiny disturbances tunnel through barriers, echoing the primordial fluctuations that might have sparked existence itself. Then there's quantum simulators, like the ones at the Center for Quantum Technologies in Singapore. These aren't your average computers, they're designed to replicate quantum systems so complex that even supercomputers struggle with them. By engineering controlled environments, scientists can watch particles tunnel in ways that mirror cosmic events, offering clues about how space-time itself might have emerged from a quantum jump. And let's not forget tabletop experiments with ultra-cold atoms. By trapping atoms in laser grids and tweaking their energy states, physicists can recreate the conditions of a tunneling event down to the smallest detail. It's like building a miniature universe in a lab where every flicker of quantum behavior holds a secret about the grandest scales. What's thrilling is how these experiments bridge the gap between theory and reality. They're not just testing ideas, they're giving us front-row seats to the quantum drama that could have birthed everything we know. And as these tools grow more sophisticated, who knows what cosmic mysteries we'll unlock next? Up ahead, we'll explore the philosophical rabbit hole this opens. What does it mean if our universe truly began with a quantum accident? Stay curious. Now, let's take a step back and ask the bigger question: what does it all mean if our universe began as a quantum fluke? If existence itself is the result of a random tunneling event, how does that reshape our understanding of free will, purpose, and even reality? Consider the age-old debate between determinism and free will. Classical physics once painted the universe as a giant clockwork where every event was predetermined by the ones before it. But quantum tunneling throws a wrench into that idea. If the birth of the cosmos was a probabilistic jump, not a fixed outcome, then maybe the universe isn't as predictable as we thought. Suddenly, the idea of free will doesn't seem so outlandish because at the deepest level, reality might be built on uncertainty. This brings us to existentialism, the philosophy that argues we create our own meaning in an indifferent universe. Thinkers like Jean-Paul Sartre claimed that without a predetermined purpose, humans are condemned to be free, forced to define their own path. Quantum indeterminacy eerily mirrors this idea. If the universe itself emerged from a random quantum leap, then perhaps our lives aren't scripted by fate but shaped by countless tiny probabilities, just like the particles that tunneled us into existence. But here's the twist: does randomness equal meaninglessness? Not necessarily. Some physicists argue that quantum accidents might actually be the source of creativity in the cosmos. Without that initial unpredictability, stars, galaxies, and even life might never have formed. So instead of a cold, mechanical universe, we might live in one where chance and choice dance together, where every decision we make adds to the unfolding story of reality. It's a dizzying thought that our search for purpose might be woven into the same quantum fabric that birthed the cosmos. And as we push deeper into these questions, we're not just exploring physics, but the very nature of what it means to be here at all. Up next, we'll look at where this science is headed, the cutting-edge research that could rewrite our cosmic origin story once again. Stay with us. Now, let's turn our gaze toward the horizon of discovery, where science is pushing the boundaries of what we know about quantum tunneling and the birth of the universe. One of the most exciting frontiers is string theory's so-called swampland, a collection of ideas that might help us distinguish between viable theories and dead ends. Imagine this as a cosmic filter, separating theories that could describe our universe from those that simply don't fit. Researchers are exploring whether certain quantum tunneling scenarios could survive this swampland, potentially narrowing down how our cosmos emerged from the quantum foam. Meanwhile, quantum computing is stepping into the realm of cosmology, offering a revolutionary way to simulate the early universe. These powerful machines could model quantum tunneling events with unprecedented precision, giving us virtual glimpses into how space-time might have first flickered into existence. Think of it as running a cosmic experiment in a supercharged digital lab, one that could reveal whether our universe's birth was a rare accident or an inevitable outcome of deeper physics. And then there's the James Webb Space Telescope, our newest window into the ancient cosmos. By peering back at the universe's earliest light, it could uncover clues about whether quantum tunneling left fingerprints in the cosmic microwave background or the formation of the first galaxies. Every snapshot from this telescope might bring us closer to answering whether our universe's origin was a singular quantum jump or part of a grander, multiversal pattern. What ties these threads together is the thrilling possibility that we're on the verge of breakthroughs that could redefine reality itself. Whether it's through theoretical leaps, quantum simulations, or telescopic revelations, the next decade of research promises to rewrite the story of our cosmic beginnings. And as we piece together these clues, we're not just uncovering the past, we're shaping the future of how we understand existence. Coming up, we'll wrap up our journey with a look at the wildest implications of these theories and why they matter not just to physicists but to all of us. Stay curious. As we bring this cosmic journey to a close, let's take one last look at the mind-bending ideas we've explored. Could our universe be a rare quantum fluctuation, a Boltzmann brane hallucinating its own existence, or perhaps a holographic projection tunneling from a two-dimensional boundary? Maybe it all began with colliding branes in a higher dimensional space, or as a white hole erupting from the remnants of another cosmos. Each of these theories stretches our imagination to its limits, challenging everything we thought we knew about reality. What's truly remarkable is how these ideas bridge the gap between the infinitesimally small and the unimaginably vast. Quantum tunneling, a phenomenon once confined to the realm of subatomic particles, might hold the key to the universe's very first moment. Whether through loops of space-time, vibrating strings, or cosmic wormholes, the possibilities are as thrilling as they are humbling, and that's the beauty of science, it's never finished. Every answer leads to new questions, every discovery opens another door. As Carl Sagan once said, somewhere, something incredible is waiting to be known. So keep wondering, keep exploring, and who knows, the next great cosmic revelation might come from you. If you've enjoyed this dive into the universe's deepest mysteries, don't forget to hit that like button and subscribe for more mind-expanding content. Turn on notifications so you never miss an update, and let us know in the comments which theory blew your mind the most. Until next time, stay curious, because the universe still has plenty of secrets left to share. Now, before we wrap things up completely, here's a little secret, my personal favorite from all these wild theories. If I had to bet on how the universe began, I'd put my money on the holographic wormhole idea. Picture this: our entire cosmos, with all its galaxies and black holes, might just be a projection tunneling out of a two-dimensional boundary, like some cosmic mirage. It's the kind of idea that feels equal parts science and science fiction, and that's exactly why I love it. But here's the fun part. I want to hear your pick. Did one of these theories stick with you more than the others? Maybe you're convinced the universe is a Boltzmann brane's daydream, or you're all in on colliding branes. Drop your favorite in the comments and let's debate. After all, the best part of exploring these ideas is realizing how many ways there are to wonder about the universe. And hey, if you've got a theory of your own, even a wild one, share that too. Who knows, you might just spark the next big cosmic conversation. Thanks for joining me on this journey through the quantum unknown. Stay curious, keep questioning, and I'll see you in the next adventure.